Heartspeed is a recently discovered vulnerability that turns power sidechannel attacks into remote timing attacks with frequency scaling. When the workload consumes more power, as shown by the blue trace in this figure, the processor runs at a lower frequency, resulting in longer program runtime observable through remote timing analysis. This challenges decades of research on mitigating both power sidechannel attacks and remote timing attacks. However, the effectiveness of Heartspeed has only been demonstrated on older x86 processors where frequency scaling is the primary and perhaps the only power management mechanism to keep the system below power and thermal limits. In contrast, modern x86 architectures have multiple, more sophisticated such mechanisms. Indeed, if you run the same workloads on a modern x86 processor, we observe no frequency side channel leakage as the frequency consistently oscillates around the same value regardless of the power consumption of the workload. So it remains unclear whether turning power into timing is still feasible on these processors and whether power management mechanisms beyond frequency scaling create new leakage channels. In this work, we demonstrate that not only is turning power into timing still feasible on modern x86 processors, but also that it is actually more effective and works in the absence of frequency side channel leakage. As you'll see, this enables leaking cryptographic keys from constant time code up to 5 times faster than Heartspeed has shown on older x86 processors, and our attack is effective even when the frequency of the active cores is constant. Our discovery takes advantage of Intel Thread Director, a hardware optimization that gives hints to the operating system for the scheduler to place threads on the most appropriate cores. The process gives several types of hints, but in this talk, I'll focus on the thread director table component, which reports the capabilities of each core, such as its performance and energy efficiency. I'll first explain the power-dependent system behavior that we observed through reverse engineering, and then talk about its security implications. We reverse engineer through the following methodology. We introduce a workload that is composed of multiple threads for the operating system to schedule, and while running this workload, we measure the CPU frequency, the hints that the processor provides, and how the operating system uses those hints for scheduling threads. We specifically run this experiment on Windows as it is currently the only operating system that supports Intel Thread Director, and we run it on various workloads consuming different amounts of power to observe the power-dependent system behavior. Our first observation is that when the frequency of at least one core goes below a certain value, the processor shows cores with all capabilities set to 0 called idling hints starting from the first core. These hints are power dependent, and as you can see, when a workload consumes more power, as shown by the blue trace in this figure, the processor shows idling hints on the first few cores more often. Our second observation is that when the processor gives idling hints on certain cores, the operating system does not schedule any threads on those cores, making those cores idle. Since the idling hints provided by the processor is power dependent, how the scheduler uses the cores is also power dependent. And notably, the differences in the number of cores used by the scheduler turn into differences in program runtime. The higher the power, the more idling hints is provided by the processor, and the less cores are used by the scheduler, resulting in longer program runtime. This enables turning power side channel attacks into remote timing attacks, and we call this vulnerability schedule disclosure. We run additional experiments to measure the CPU frequency while running these workloads and observe that the program runtime is power dependent in the absence of frequency side channel leakage. The figure at the bottom shows the results of the experiments, and you can see that for each core, the frequency of consistently oscillates around the same value, regardless of the power consumption of the workload, and thus we can confirm that the program runtime is power dependent in the absence of frequency side channel leakage. In the paper, we further show that the program runtime is power dependent even when the frequency of the cores is constant, and also reverse engineer the cross-component data leakage when the GPU is active. So please check out the paper for further details. Now that we know the power-dependent system behavior, let's talk about its security implications. We target Cloudflare's cryptographic implementation of site written in constant time code. And prior work has shown that each bit of the secret key can be inferred by measuring the power consumption while encapsulating a specially crafted ciphertext. As the processor power consumption affects the process idling hints, changing the scheduler behavior and ultimately the program runtime, we can leak the cryptographic key through a remote timing attack in the absence of frequency side channel leakage. We achieve an end-to-end full key recovery 5 times faster than what Herspeed has shown previously. In this work, we introduced a new class of side channel tags called scheduled disclosure that turns power side channel tags into remote timing attacks without frequency scaling. As Herspeed, our attack shows that analog level leakage is in scope when considering timing attacks, and this cannot be mitigated through constant time code. However, our attack is 5 times faster than what Herspeed has shown on older x86 processors and works in the absence of frequency sideshow leakage. Therefore, future mitigations should consider all sources of leakage that turns power into timing, not just the frequency sideshow leakage. And with that, I'll conclude my talk. Thank you.